All right, let's dissect this paper on rejection sampling IMLE for few-shot image synthesis. The authors tackle a common problem, generating high-quality images with limited training data. What's the core innovation here, from your perspective?
The core innovation lies in addressing a latent space misalignment problem inherent in existing implicit maximum likelihood estimation, IMLE, methods. These methods often struggle because the latent codes selected during training don't match the distribution of codes sampled during inference. This leads to poor generalization and low-quality generated images. RS-IMLE solves this by cleverly modifying the prior distribution used during training.
So IMLE itself isn't novel. It's the application and the modification of the prior that's the key contribution. Can you elaborate on this misalignment problem? Why does it occur in the first place?
The misalignment stems from how IMLE selects latent codes during training. It picks the codes that produce generated images closest to the training data points. This leads to some regions of the latent space being consistently undersampled during training, even if they have high probability under the standard normal prior, often used. During inference, when samples fall into these undersampled regions, the results are poor. It's a sampling bias issue.
And this is where the rejection sampling comes in. How does it help realign the training and inference latent code distributions?
Rejection sampling allows us to shape the prior distribution used for training. Instead of directly sampling from a standard normal distribution, we sample from it and then reject samples that are too close to the training data. This forces the model to explore more of the latent space during training, leading to a better match with the inference distribution. The key hyperparameter here is epsilon, which defines the rejection threshold.
Interesting. So you're essentially creating a new non-standard prior distribution implicitly through rejection. How is this new prior defined mathematically? Is there a closed form expression?
There isn't a closed form expression for the resulting prior. The paper derives a relationship between the cumulative distribution functions, CDFs, of the distances between data points and their nearest neighbors during training, and randomly sampled latent codes. This relationship guides the design of the rejection sampling procedure, but the resulting prior is defined implicitly through the sampling process.
The paper mentions a theoretical analysis justifying this approach. Can you summarize the key theoretical insights?
The analysis shows how the CDF of the distances to the selected latent codes during training differs significantly from the CDF of distances to randomly sampled codes during inference. This difference is amplified as the number of samples increases. By using rejection sampling to create a new prior, the authors aim to reduce this discrepancy, leading to better alignment between training and inference.
The paper uses FID, Frechet inception distance, as a key evaluation metric. Why is FID particularly suitable for this few-shot image synthesis problem?
FID is a good perceptual metric that assesses the similarity between the distribution of generated images and the distribution of real images. In few-shot settings, where the training data is limited, it's crucial to ensure that the model doesn't just memorize the training examples, but learns a broader representation of the data distribution. FID helps evaluate this aspect.
The results show significant improvements in FID compared to baselines. What other metrics were used, and what did they reveal?
Besides FID, the authors also used precision and recall metrics to assess the model's ability to generate diverse and realistic images. RS-IML consistently achieved near perfect precision, meaning most generated images were realistic, and significantly higher recall, meaning it covered a wider range of the data distribution compared to baselines.
The paper also includes qualitative results showing visual comparisons of generated images. What were the key observations from these qualitative evaluations?
The qualitative results visually confirm the quantitative findings. RS-IML generated sharper, more diverse, and more realistic images compared to the baselines. The authors also introduced a visual recall test, where they used real images as queries to find the closest generated images. RS-IML consistently produced visually similar and diverse results, highlighting its superior mode coverage.
The paper mentions an ablation study on the hyperparameter, or what insights did this ablation provide?
The ablation study showed that the performance of RS-IMLE is sensitive to the choice of OR. Optimal performance was observed for values around 0.15, with performance degrading as OR deviated significantly from this value. This highlights the importance of careful hyperparameter tuning for this method.
What are the limitations of RS-IMLE? Are there any potential drawbacks or areas for future improvement?
One limitation is the computational cost associated with rejection sampling. Rejecting samples can slow down the training process. Also, the optimal value of ORIC might vary across datasets, requiring careful tuning. Future work could explore more efficient sampling strategies or adaptive methods for determining E.
How does RS-IML compare to other approaches that address the few-shot image synthesis problem, such as those based on GANs or other generative models?
Oh. The paper directly compares RS-IMLE to several state-of-the-art few-shot image generation methods, including those based on GANs. RS-IML consistently outperforms these baselines in terms of FID, precision, and recall, demonstrating its effectiveness in addressing the challenges of few-shot image synthesis.
The authors use a specific generator network architecture. How crucial is this architectural choice to the success of RS-ML? Could it be applied to other architectures?
The paper uses a generator network based on VDVAE decoder modules. While this architecture works well, the core idea of RSML modifying the prior distribution through rejection sampling is not tied to a specific architecture. It could potentially be applied to other generative models as well. The ablation study on latent dimensions supports this, showing that even with fewer parameters, RSML outperforms baselines.
So, to summarize, RS-ML offers a novel approach to improve few-shot image synthesis by addressing a latent space misalignment problem through rejection sampling. It demonstrates superior performance compared to existing methods, but further research is needed to optimize its computational efficiency and hyperparameter tuning. Thank you for this discussion.